Welcome to the third lecture of the course Mathematical Finance. And this week we will be talking about martingales and risk-neutral measures, and we will largely be using the material from chapter 6 from the book of Yoshi. So I'm going to do a very small recap, very high level of some measure theory. So when you work with a discrete random variable, like you do in the binomial tree, you have discrete events like the probability of throwing a die, and then you can throw a 1 or a 2 or a 3 up to a 6. And then to each of these discrete events, you can give a probability. And of course, when you move to a continuous random variable, now you have to introduce this concept of probability density. And if you go from the real line to an even larger space, which we usually denote by the Greek letter capital omega, then we can generalize the notion of a probability density function to what's called a measure on a probability space. And the way that it's formalized is by saying, if I select a set, capital A, which is a subset from that space, going back to the real line, if I, for example, choose an interval on the real line, then I have kind of I don't have a single point, but if I use a set, I have kind of a thing that is big enough, so to speak, bigger than a single point. And then I can really say for the set A, I can then define what is the probability of landing in that particular set. And that probability is then a real number. And if I can do this for any set, I can kind of generalize this to the probability measure. And let's say if I use a floppy notation, if I have kind of an infinitesimal element dz in my probability space, then I can kind of define the probability density function with respect to landing in that infinitesimal element dz. And of course, if we choose a real line, that is a valid example of a probability space. And formally, you would say for each interval on the real line, I can define a real probability. And then I can then generalize this as integrating over the real line. For each infinitesimal element dz, I then multiply with a probability density function, for example, of the standard normal random variable. Last week, we introduced Brownian motions, and I'm going to be spending a bit of time on maybe the most important tool that we have in kind of working with Brownian motion, and this is known as Girsano's theorem. And what does Girsano's theorem do? It makes a connection between changing the drift of your Brownian motion and changing the probability measure on the space where you are working. And I'm going to look at the following question. Suppose that we have Brownian motion with drift. So we have W tilde that has a drift mu dt. And I want to compare that to a Brownian motion without drifts. And then the question is, can we find a probability measure tilde such that the original Brownian motion under the measure P becomes this Brownian motion with drift under the new measure? The way of doing that is by saying, let's consider a time step delta t. And then I'm going to look at the change in the Brownian motion over that time step delta t. And I'm going to abbreviate this with delta w. And then I can ask myself, if the Brownian motion has a drift, then the probability density function of going one step ahead in time under the measure P tilde is Brownian motion minus the drift mu delta t squared divided by the variance of the Brownian motion is delta t. If there is no drift, then the Brownian motion has a normal distribution with mean 0. and with variance delta t. And we see the normalization constants because the variance stays the same, the two Brownian motions, or in the two different views on the same Brownian motion. That's maybe even more correct to say it that way. I have the same Brownian motion, but I have two different ways of viewing that thing using a different probability measure. Both views on the Brownian motion have the same variance, so this normalization constant drops out. And if I take the ratio of these two numbers, I am dividing the exponential in the numerator with an exponential in the denominator. And I can basically subtract the two arguments in the exponential. And again we are doing, when we are manipulating with normal distributions, we are always playing this completing of the square trick. So we are doing this again. So I can work out this quadratic form, delta w minus mu delta t squared as delta w squared minus 2 delta w mu delta t plus mu delta t squared. Now I see that the delta w squared term in the numerator and the delta w squared term in the denominator cancel against each other. And there is this big expression, which looks a bit daunting, actually simplifies into something very nice and clean. It is the likelihood ratio of these two things simplifies to the exponential of mu times delta w minus 1/2 mu squared times delta t. And when I saw this the first time, I was quite confused, or I found this difficult to get my head around this. So likelihood ratio is like difference between two probability density functions. Then if we do this computation, you see that this likelihood ratio is itself a function of the Brownian motion process. So what's then the conceptual step that you can make is that you say, well, this likelihood ratio, because it is a function of the Brownian motion, likelihood ratio itself is a stochastic process. The likelihood ratio itself is a random variable. And a likelihood ratio is always a random variable with mean 1. Why should you always have mean 1? Well, if you take the likelihood ratio does is it's basically redistributing probability mass, but the probability density function must always integrate out to 1. So if I take the expected value of a likelihood ratio, I am starting with something that integrates out to 1, and I will end up with something that integrates out to 1. So a likelihood ratio must be a strictly positive random variable that has mean equal to 1. So now in the previous slide, we just took a look at a single time step delta t. What happens if we now take a whole path of the Brownian motion with all time steps delta t, delta t, delta t, delta t? Now we're going to use another useful property, or an important property of Brownian motion, is that all these increments are independent from each other. So what is the likelihood ratio of a whole path if I take all these delta t increments? Well, that is the product of all those one-step likelihood ratios. And if I take a product of exponentials, again, I can take this product inside the exponential as a summation. So this becomes the exponential of the summation of all these steps. So now I'm integrating mu against delta w. And here I'm just integrating mu squared against delta t. And again, proof by hand waving, if we let the step size delta t become smaller and smaller and smaller, this first summation, mu I against delta w, becomes a stochastic integral. And the second summation, minus 1/2 mu squared times delta t, becomes a normal integral against time. So we have the following representation for the, if I have a stochastic process mu, because I can change my mu for each time step delta t, and even maybe for each value of the Brownian motion. So mu itself can be a stochastic process itself. Then the Radon-Nikodym the likelihood ratio process can be expressed in this form as the integral over mu dw minus 1/2 mu squared t. Again, this usually you only see this formula here, and this comes a little bit falling from heaven, but hopefully I've given you a bit more intuition. Again, it is the same completing the square trick, or in this case, not completing the square, but separating the square, that you get this nice linear form, which kind of follows from the quadratic form of the Brownian motion, and then that the delta W squared term just drops out, and then you are just left with the cross term and the quadratic mu delta t term. So quantity, this likelihood ratio, as a stochastic process itself, is known as the Radon-Nikodym derivative. So now we can kind of play our game in two directions. I can say, if I want to change the drift of the Brownian motion, I can kind of derive what the stochastic process looks like. That's basically the proof I've given it to you in the previous slides. But again, we can go in the other direction as well. If you give me a stochastic process that is strictly positive and has mean equal to 1, it is therefore a valid likelihood ratio change process, and I can use that process to then compute what is the implied change of drift of the Brownian motion. The Radon-Nikodym process itself is a stochastic process based on the Brownian motion. It has for each time step a local volatility equal to this change of drift mu of s, and a Radon-Nikodym derivative is always a martingale under the original probability measure P with a mean equal to 1, and it is a strictly positive stochastic process. I haven't put that down here, but as it is the likelihood ratio of two probability density functions, and probability density functions themselves are strictly positive, the Radon-Nikodym process also must be strictly positive. And again, you see this because I'm taking this exponential here. That is also that also guarantees that the Radon-Nikodym derivative is a strictly positive stochastic process. So now we get to Gersano's theorem. Gersano's theorem basically makes the connection two ways. It says that if I have a well-behaved stochastic process, and well-behaved kind of means that the new process doesn't explode to infinity and that you have some finite moments, but we will never run into an example where the new process is not well-behaved. So as a reasonable approximation, we can say for any stochastic process nu, we can then construct a Radon-Nikodym derivative by saying I take the stochastic integral of the process nu with respect to the Brownian motion, and I compensate with minus 1/2 mu squared. Then this thing is a martingale under the original measure P, and the new process that is sitting here is the process that says if my original Brownian motion minus nu dt, that process with drift becomes a Brownian motion, a standard Brownian motion without any drift under the new measure P tilde. And for more details, you can look in the book by Yoshi in Theorem 6.1, where he also talks about Gersano's theorem. So again, the way we are going to use this is we're going to say if I see a positive stochastic process that is a martingale and has high expectation equal to 1, I can kind of see what, if I know the volatility of that Radon-Nikodym martingale, I then can use that volatility, the constant or volatility stochastic process, and that volatility stochastic process can then be used to remove a component, a drift component nu t omega from my original Brownian motion and make that into a new Brownian motion W tilde. So here I'm going to arrive at what I believe is a super important slide, and that's why I've made it mostly in red, because I'm going to be using this a lot throughout the rest of the course. And this isn't, let's say Yoshi doesn't have this explicitly in his book. You can kind of read it in between the lines, but I think this is super important, and basically I would almost say learn these steps by heart, because it will be very useful for the rest of the course. What I'm going to do here is, what is the general scheme for doing a no arbitrage pricing? And the general scheme is, in the first step, we will choose a numeraire asset, which I denote now by N sub T. Basically, I have a freedom to choose whatever numeraire asset is nice to work with or convenient to do the computation. So there is a degree of freedom here, that I am free to choose whatever numeraire assets I like. And we're going to using that later in the course, because then for more complicated options, it really turns out to be helpful to make a clever choice of your numeraire assets. Can I choose anything that I want? No. First of all, the numeraire asset must be a traded asset in the economy, and it must have a strictly positive price. The price is equal to 0, because we're going to divide by the numeraire asset. Division by 0 doesn't work. So I can choose whatever numeraire asset that I want, but it must be a traded asset in the economy, and it must have a strictly positive price. If I have chosen my numeraire asset, I can then check the existence of a martingale measure. And how does that work? You see that the measure has a superscript n, so the choice of measure belongs to the choice of numeraire. This is kind of a new element, or let's say, if in the classical Black-Scholes theory, people talk about the risk-neutral measure, and I don't like that terminology, because there is a deeper connection where you say, first choose the numeraire, and then you divide all the prices of all the other traded assets in the economy by this numeraire, and then you check whether in your model of the economy, all the relative prices of all the other traded assets divided by the numeraire, whether they become martingales. If it is possible to find at least one such martingale measure, you have already proven that the economy is arbitrage free. This is the fundamental theorem of arbitrage pricing. Better, if there is only one possible way to construct this martingale measure, so if the martingale measure is unique, it turns out that the economy is arbitrage free and complete. Completeness means that any possible derivative that you have in this economy can be replicated with a replicating portfolio and with a unique trading strategy. If you have found such a martingale measure, and you know that the prices of all other traded assets in the economy divided by the numeraire are martingales, I can then use this martingale property to compute the price of a derivative, the particular payoff. Because the derivative with a certain payoff divided by the numeraire, so if I have a payoff at time capital T, the payoff is f of s at time capital T divided by the numeraire, that thing is a martingale. So that means that today's price, f small t divided by the numeraire times small t, must be martingale measure, the conditional martingale, it must be the conditional expectation of value at time capital T. And basically what I'm using here is just a definition of a martingale. It means it's not going up, it's not going down on average. So the expected value of where the process is going to be in the future is today's value. And normally you kind of use it by saying, I know where the process is today, and then I'm going to impose this as a restriction on the process at the future date. Here we are using it the other way around, saying, I know what the payoff is at some time capital T. Then using the martingale property, I can then compute what the value of the process today at time small t should be. So these steps 1, 2, 3 are basically the most important ones, and I've made them in red. And when we are in a complete market, then we can use a step 4. If we are in a complete market, i.e. when the martingale measure is unique, then there is a unique replicating portfolio, and then we can use the martingale representation theorem, which I already talked about last week, to explicitly compute what the delta hedge looks like. And the delta hedge is this partial derivative of the price formula at time small t divided by any of the underlying assets. Here it's a one-dimensional, but if I have derivatives that are a function of multiple underlying assets, I can basically take partial derivatives with respect to each of these underlying assets. And this gives me a gradient or a vector of derivatives. And I then simultaneously know how much to hedge in each of the underlying assets at the same time. So let's use this new theory. Again, go back to the Black-Scholes model, but now we're going to use kind of the martingale measure approach to doing Black-Scholes. So this is different from the partial differential equation approach that we discussed last week. So in the Black-Scholes model, in the Black-Scholes economy, there are two traded assets only in the economy. We have a stock that follows the geometric Brownian motion, mu s dt plus sigma s dw. And we see the drift mu. So this is the behavior of the stock price in the real world with an expected return of 4% or 6%. Then we have a bank account. And in the standard Black-Scholes model, the interest rate is a constant. The bank account is risk-free bank account. So my money, if I put money in the bank account, it grows continuously with a risk-free growth rate of equal to R, and R is a constant as well. And now the question is, can we compute the price of a call option to pay off at time capital T of max st minus k, 0? So we're going to apply the steps here. And step one is choose a numeraire. Well, in the Black-Scholes economy, there are only two assets that are traded in the economy. There's not much to choose there. And the standard choice for choosing your numeraire is to choose the bank account as your numeraire. If we choose the bank account, we should check whether a martingale measure exists. There are not that many other assets, so the only thing that needs to become a martingale is the ratio of the stock price over the bank account. I can apply Ito's lemma to S over B as a stochastic process. And because B is a deterministic process, it basically means that the drift rate becomes mu minus R times S over B, plus sigma times S over B dW. Now the question is, how do I make this thing into a martingale? Well, I can apply a change of measure, and if I apply a change of measure, then my original Brownian motion under the real world measure P becomes a Q Brownian motion. It should be a Q superscript B, if I'm very precise in my notation, with a change in drift minus kappa delta T. What if I apply this? I multiply the minus kappa with sigma, and then the drift term under the new measure becomes mu minus R minus sigma kappa plus sigma, and then I'm using my Q Brownian motion. What makes the relative price process martingale? Well, then this drift term should be equal to 0, because mu and R are constants and sigma is a constant. There's only one possibility to make this thing a martingale, is to choose kappa equal to mu minus R over sigma. And this is a quantity that is known to economists. This is known as the market price of risk. But for here, don't worry that much about the interpretation. We are just saying, yes, we can make the relative price of the stock price over the bank account. We can make this a martingale by making sure that mu minus R minus sigma kappa becomes equal to 0, and there is only one choice for kappa to make this work. That's this choice here. And therefore, we have proven two things at once. First, we can find a martingale measure. So therefore, we know that the Scholes economy is arbitrage free. And there is only one possible way to make the stock price into a martingale, and therefore the martingale measure is unique, which means that the Black-Scholes model is arbitrage free and complete. The completeness means that every possible derivative that is a function of stock in the bank account, I can price uniquely because I now have this unique choice of this martingale measure. So I'm now interested in computing a derivative, and I'm going to compute this derivative in the martingale way by saying I know what the payoff is at time capital T. If I divide by the bank account value at time T, then this relative price of the call option payoff divided by the bank account is a martingale. And therefore, the price of the call option divided by the value of the bank account times small t is just the Q expectation of the payoff. And I can bring this B inside the max by saying I want to take the Q expectation of S divided by B time capital T minus K divided by B at time capital T. How do we compute this expectation? Well, the relative price, stock price divided by the bank account is a martingale. And it is a martingale with constant volatility equal to sigma. I have the representation that S over B is e to the power minus 1/2 sigma squared T sigma times the Brownian increment. And when is this thing in the money? When is S capital T larger than K? If and only if I can take logarithms here on the left and the right and shift some terms around. If the Brownian increment is larger than the log of KB over BS minus 1/2 sigma squared T minus T. Let's now introduce a new random variable capital Z, which is sigma times the Brownian increment. Then Z has a mean of 0 and a variance of sigma squared T minus T. And I now need to integrate to compute the expectation. I integrate over the positive part of all the payoffs. So that is the integral from D going to infinity. And D is this logarithm of KB over BS plus 1/2 sigma squared T. So D is exactly this point where the option is at the money, and above that, the option will be in the money. So I'm integrating over all these positive parts of this thing here as a function of Z minus this probability density function Z. And as I showed in the tutorial, I can split this integral into two parts. I can take the integral over with respect to the constant K times this probability density function, and that becomes this constant K over dt times the normal density function evaluated at minus D divided by sigma square root T minus T. The other part is a little bit more complicated. I have this Z sitting in the exponential. I have a Z squared sitting in the exponential here. I can basically put these two terms together, and I can use a completing of the square argument. And then I have a constant times a new probability density function, but now the mean has shifted from mean 0 to mean sigma squared T minus T. So therefore, the first integral, the part 1 integral, is the cumulative normal distribution evaluated at D over sigma square root of T, but D minus sigma squared over sigma square root of T. And if I put everything together, I get the first part here, I get the second part here, and again, you see that this is the option price divided by the bank account. So we are in these martingale calculations, we are always doing relative prices. So this is a mistake that many people made, is they worked so hard to do this computation and then they say, oh, we are done. But then no, it's still an error, because you have computed the relative price. And of course, if you want a price, you want something in euro terms. So to get the price in euros, you need to multiply both sides by b of small t. Then really get, well, if you multiply by b of small t, then that cancels this term here. Here you get the ratio of b small t over b large T. And then because the interest rate is constant, you get the famous Black-Scholes formula of S small t times n d1 minus k times e to the power minus rt minus t times the n of d2. And this is the famous Black-Scholes call option formula. Now, not from the partial differential equation or the heat equation, but by explicitly doing the integral and doing the martingale version. And again, I will keep pressing on this. It looks like we are doing a discounted expectation. A more correct interpretation is by saying it's not discounting that we are doing. What we have actually done is we did the computation by dividing by the numeraire asset, which is the bank account. When interest rates are constant, discounting, you are kind of free to take the discounting inside or outside of the expectation operator. When interest rates are stochastic, it's really important to realize that we have this numeraire asset. If this thing is a stochastic quantity by itself, then it's, of course, it's really important to have realized that this numeraire, stochastic numeraire thing is sitting inside the expectation operator, and covariance of the numeraire and your option payoff is an important part of doing your expectation computation. In the Black-Scholes case, when this thing is deterministic, then you do no harm, and you accidentally do the right thing by putting that deterministic quantity b of t outside of the expectation operator. But in general, when the thing in the denominator is itself a stochastic process, it's really wrong to pull that outside of the expectation operator too early. And we found the Black-Scholes formula, and because the Black-Scholes economy is a complete market, because there is a unique martingale measure, it means there is a perfect replicating portfolio. This perfect replicating portfolio we can construct via the delta hedging by taking the price formula f of small t and then taking the derivative with respect to the underlying risk driver, which is in this case s of small t. We can compute this delta explicitly, and it looks like we just took the derivative with respect to this s here, which is not the case, because you see the small s, or sorry, the s of small t sitting here and the s of small t sitting here. When you are taking this derivative f with respect to s small t, there will be three terms in your calculation. So this nd1 term times the s times the partial derivative of the nd1 term with respect to s. And the third term is minus k minus the discounted k times the partial derivative of your capital N with respect to this s. And then it turns out that this additional second chain rule term and this third chain rule term exactly cancel against each other, and we are left with this first term only. So let's talk a bit more about these numeraires and this additional degree of freedom that you have in choosing these numeraires, because we can play with this and we can use this to our advantage in a lot of calculations that we are doing. So in the step one, or in my step one, I said you can choose any numeraire as long as it has a strictly positive price and is a traded asset in the economy. Don't we have a problem here? If I do my option calculation with numeraire n, if I do also an option calculation with numeraire number m, how do I make sure that these two prices are actually the same? It should be highly inconvenient when my price that I calculate depends on my choice of numeraire. So ensure that these prices are correct, or the way that the mathematics work is that there is a very specific relationship between these two martingale measures. So if I change a different numeraire, then I will have to use a different martingale measure. The relationship between these martingale measures is exactly compensates the change in my choice of numeraire. So the prices that I'm getting guaranteed to be always the same price, irrespective of whatever numeraire I like to work with. So because when there exists a martingale measure, I know that the economy is arbitrage free, and that means that prices for derivatives are unique. They should not depend on the choice of numeraire. So therefore, I can express the same value V0. It should be a V sub t here. I can express the same value V sub t just by saying it is, I can choose n as my numeraire, and then take the expectation of the P of x capital P using the Qn probability measure. And then to get it back to euros, I must multiply with today's value of the numeraire and small t. This must be the same answer as by saying I could also have chosen a numeraire m, divide all my prices by m. If I then take an expectation under my Qm probability measure and multiply with numeraire m times small t, these two values must be equal to each other. All valid choices of numeraire. So therefore, if I bring this inside the expectation, I can say that the Qn expectation of my payoff x capital T divided or multiplied by n small t divided by n big T. I've only taken the n of small t inside the expectation operator, which is allowed because I'm doing this relative to the information at time small t, and I know what n of small t is at time small t. And I can bring this m inside here. Then I can multiply and divide with the same quantity. So I have an m of big T here and an m of big T here, and an n of big T here. Sorry, and an m of small t here and an m of small t here. I'm still working under the n probability measure. And then I am basically multiplying and dividing with the same quantity. So basically this term here becomes equal, is equal to 1. Now I'm going to shift the parentheses around because now I have my m big T in the numerator. So I can shift that here. Then I have this cross product here of n small t over n big T, m big T over m small t. This term here turns out to be strictly positive and has an expectation equal to 1. And therefore, this is a valid Radon-Nicodim derivative. And this exactly Radon-Nicodim derivative is the one that I can choose to go from probability measure Qn to probability measure Qm. And by constructing these different probability measures in this way, then I am guaranteed that if I choose a different numeraire, then I must adjust my martingale measure. So this is why this superscript is really important, because each different choice of numeraire implies a different choice of the martingale measure. This kind of double correspondence guarantees that the prices that I compute are always correct, no matter what numeraire that I choose. And Joshi in section 6.13 also shows this result that the Radon-Nicodim derivative of changing from martingale measure Qm to martingale measure Qn is this ratio of numeraire processes. And the way that I adjust my Brownian motions is that the volatility of the numeraire ratio process is kind of what I need to adjust the drifts of my Brownian motion to go from one martingale measure to the other martingale measure. This is a bit complicated stuff, especially if you see this for the first time. So let's do the Beck-Scholes model once more, now explicitly with this kind of change of numeraire machinery. So I am interested in computing the derivative value f of time small t, which is the bank account at time small t times the QB expectation of S over B big T minus K over B big T. And I can view this max operator also, or I can rewrite the max operator by saying it is S minus K, provided that S is larger than K. So this capital I is the indicator function that a certain event happens. So if S is larger than K, this indicator function is equal to 1. And if this event is not true, this indicator function is equal to 0. Then if S is larger than K, I am multiplying by 1. I'm getting S minus K. If S is smaller than K, this event is not true and I'm multiplying by 0. But this representation of S minus K times the indicator function that S is larger than K is another way of writing this max operator. But the advantage of doing this multiplication with the indicator function is I can now split my expectation, saying it's the expected value of S over B times the indicator function minus K times the expectation. S is larger than K. Now I can split this into two parts. K is a constant. Therefore, the expectation of an indicator function, taking an expectation of an indicator function, is computing a probability. So the second part is k times the ratio of the bank account values times the Q probability of the event S is larger than K. And the part 1 calculation we did with this integral. Another way of looking at this is by saying I have this S capital T divided by B capital T. If I multiply and divide by S small t and B small t, I get this new change of numeraire ratio. I'm going from the B as my numeraire to the stock price as my numeraire. Therefore, I can do my change of measure. I can represent this expectation as the expectation of the indicator function under the S probability measure. So an S probability measure is kind of shorthand for the Q superscript S probability measure. So this is the martingale measure that belongs to taking the stock price as the numeraire. And taking the stock price as a numeraire is a valid choice of numeraire because the stock price is a traded asset in the Black-Scholes economy, and the stock price has a strictly positive price. So now I'm getting a general formula for my call option price. As the call option price is the price of the stock times the S probability of the event S is larger than K, minus the discounted stock price, sorry, the discounted strike price times the Q probability of the event that S is larger than K. And I think this formula is really nice because in this derivation here, we did a change of probability measure, but we haven't used that the stock price must be exactly a log normal distribution. And it turns out that this representation of the call price is a general representation for any possible distribution of the stock price. That I think is a very interesting insight, is that the structure of S times ND1 minus K times ND2, N1 and N2 are probabilities, and there is a much deeper interpretation and a much deeper connection, is that it is the probability of the same event that the stock price ends up in the money, but the same event is viewed under two different martingale measures. For the strike, we use the martingale measure that belongs to the bank account, the probability measure to quantify the probability of this event. For the stock price part, we use the martingale measure that belongs to the stock as a numeraire to measure what the probability of this event is. Continue with the Black-Scholes model, then we can compute the log normal Q probability of the event S is larger than K. Well, that's what we already have done. The previous slide, so the Q probability is this ND2 type of term. If we compute the S probability, we're going to do a change of measure. So we start under the bank account induced martingale measure, where the stock price follows the process RSDT plus sigma S dWQ. The numeraire ratio process S over B is a Q martingale, because that's what the definition of the Q process was. Therefore, the volatility of the numeraire ratio process is sigma. So if I now apply Girsano's theorem with this martingale process as a Radon-Nikodym derivative, I need to add and my Q Brownian motion becomes an S Brownian motion with a positive drift plus sigma. Therefore, under the stock measure, the stock price itself has a drift equal to the risk-free rate plus sigma squared. And if I solve the SDE, I need to do this minus 1/2 sigma squared correction. If I start with minus 1/2 sigma squared and I add a full plus 1 sigma squared, I'm ending up with a plus 1/2 sigma squared. So this is the solution of the stochastic differential equation of the stock price process under the S martingale measure. And therefore, the probability that S is larger than K is the probability that the S Brownian motion is larger than the log of K over S of this R plus 1/2 sigma squared. And if I substitute and work out all the terms, I am getting the ND1 term. So this is another way of deriving the Beck-Scholes option pricing formula by using this change of probability measure during the calculation. That's it, and I'm going to stop the recording. Yeah.